Okay, so good morning. All right, so for sympatric speciation to happen, a polymorphism in a population has to first arise and then be maintained. And then some reproductive isolation must evolve between these new emerging species. In this talk, I will be concentrating on the initial phase of speciation, that is, in the emergence of polymorphism. Yeah? Okay, these results are derived for populations which are sexually reproducing, diploid populations, where females choose males based on a trait which is under ecological selection. Yeah? So these are called magic traits. We assume that the population is initially monomorphic with respect to this magic trait, and that the mutations happen quite rarely, so that the population reaches its attractor before the new mutation comes along. So in here I want to stress that these results are derived without specifying the exact ecological scenario. So it is in that sense a quite general framework. Okay, so what happens to an initially monomorphic population? So there are two different types of evolutionary trees here. Just get some water. In both of them, there's first some sort of a directional selection until it reaches, in the left picture, until it reaches a point which is an evolutionary endpoint. And in the right picture, at some point this trait branches into two. So we are interested in what happens in these points, which are circled here, green. Or more specifically, we are interested whether these kind of singular points are evolutionary branching points, like on the right, or not. So does evolutionary branching happen, and what is the role of mating in this process? So in the first part, I investigate the role of associative mating, and then I contrast these results with if the mating is also dependent on the male condition. So to do this, we use this nature's model introduced some time ago, where a female encounters males randomly, and she has some maximum number of encounters per mating season. So this associative mating we model is some kind of arbitrary concave function, where the probability that she will actually pick a certain female decreases with increasing distance between their magic traits. So when they are similar to each other, the probability is the highest that the female will actually choose this male. The condition dependence we model such that the probability increases with increasing condition of a male that she will pick him, which is correlated with this genetic fitness in ecological selection. Okay. So we can construct an invasion fitness function where this Y denotes the mutant allele, and X is the allele, the monomorphic population contains only this X allele, and we see whether this mutant allele can invade. These Q's give the sexual selection components, and the small w gives an ecological selection component. It turns out that the existence of these monomorphic similarities is independent of these two types of mating, and also whether whether we converge towards these kind of singular points is also independent. However, evolutionary branching is affected by associative mating and condition-dependent mating. So in here we have a condition below, analytic condition for branching, where the small w, I'm looking left, right, so the small w gives this ecological selection component here. And if it's disruptive, it contributes a positive term. The pi gives an associative mating term, which, because it's a concave function, it contributes a negative term, so it counteracts this disruptive selection, ecological disruptive selection. But condition-dependent mating, it's an increasing function, so it again counteracts this effect of associative mating. So in a way, it's kind of strengthens this ecological disruptive selection. So just to show a graphic of these results, if you have a stabilizing ecological selection, doesn't matter on the strength of a small assortment or the condition dependence, the monomorphic population will always stay monomorphic. If there is a disruptive ecological selection, then for weaker assortment, branching is possible. If the assortment gets stronger, we will lose the branching, unless the dependence on male condition is strong. So it's stronger disruptive selection, even stronger disruptive selection, in this parameter region where branching is possible. There is a greater parameter range where this branching is possible. Okay, so it seems that associative mating hinders this kind of evolutionary branching, but dependence on male condition has a counterbalancing effect. Okay, so there's at least one problem with this kind of main-choice model, and it is that we assume that there is a fixed number of males sampled each mating season, independent of the density of the size of the population, which can of course change. So we have constructed another type of main-choice model, where in at least its simplest case, we can imagine an all-knowing female. She knows the length of the mating season, she knows the distribution of the population, genetic and density. And she chooses mates such that she wants to maximize the viability of her offspring. So in the beginning of the season, she has some initial expectation for her offspring. The mating season starts, she encounters males randomly, and when she encounters a male with whom she will have an offspring with a high viability that she would expect from future males to provide her, which she will encounter before the mating season is over, she accepts the male. Otherwise, she continues search for new males. And if the mating season ends, her expectation is zero. There's no chance to find mates anymore. So this kind of change in expectation can be described with an ordinary differential equation where rho is the density-dependent encountering rate, Bm is the frequency of a genotype M, and this epsilon M is expected viability of an offspring with male with genotype M. And how this behaves, the solution behaves, initially we have some certain expectation in the beginning of the season, E0, and then it decreases towards, when the mating season ends. So imagine that there is a male with genotype M, and she encounters this male before time tau. So you can see that her expectations from future are higher than what the male can provide her. So she refuses the male and she continues search. If she encounters him after time tau, this male provides their offspring with kind of higher viability that she would actually expect from future, so she does accept him. So this is how it works. And it turns, okay, so we can construct this invasion fitness function for this type of mating model, take the second order derivative to get this analytical branching condition. And it turns out that this kind of mate strategy does not have an effect on invasion. Yeah? So consequently, it doesn't have effect on evolutionary branching. Okay, I seem to be quite fast. So, conclusions. So at least strong associative mating is likely to evolve in a later stage of the speciation event. Yeah, so it's not likely to be in the part of the initial phase, at least not a stronger one. If there is some associative mating in the initial some previous speciation events or something like that, then some counterbalancing effect is needed. Either some condition-dependent mating, or maybe stronger disruptive selection, ecological disruptive selection. But if females use this kind of sequential search mating strategy, it does not have effect on this evolutionary branching. Alright. In good or in bad terms, of course. Alright, thank you very much.
We have plenty of time for questions. Yeah, I see one over there, where the microphone is closed. So maybe answer. So much. I cannot try to explain why this question strategy is not effective at all on branching.
So the sequential search?
Sequential search.
Yes. Well, basically, in the beginning, okay, maybe I could show this picture. So because the mating season is finite, her initial expectation, well, okay, basically all these are above the initial expectation. So basically all the genotypes will give her a higher viability than she has initially. So the mating will be essentially random, so she will just pick anyone who she encounters.
Okay, another question over there, please.
What's a bit middle between a question and a comment that's been brewing inside since yesterday. I come from a plant perspective, and I think about magic traits as having a lot of potential for plants, especially if you think about pollinator shifts, because the population adapts to a new pollinator. It's basically ecological selection, but it also results in instantaneous sortative mating. Now, there's a fundamental difference between plants and animals in the sense that, first of all, other plants don't need mates, they can self-pollinate. And secondly, they actually don't choose their own mates. And I'm just wondering whether you can comment on how those kind of differences could affect branching events, or the likelihood of evolving branching events on
You asked me if I could comment, and unfortunately, I have to say I don't know. I don't know how to answer the question.
It's probably a bit unfair to ask you this question. I could have asked anyone.
Yeah.
I'm keen to get some feedback on it maybe during the conference break, but that's all.
Maybe it would be fair to comment here that your comments or your feedback is actually one reason why maybe the term magic traits is not so well chosen, because it suggests a sort of implausibility or special conditions being required, and I think you're completely right that in some circumstances plants with a local mating radius would be among them. This is rather natural. There's no magic involved, so I personally avoid this term. Other questions? Mike?
Yeah, I've got actually a set of comments, and it applies to what you've done, and it also looks back at some of the other things that we heard this morning and yesterday. I find myself, not surprisingly, learning a lot. Much more surprisingly, I find some of the things that I wrote in 1968 being confirmed, and it being supplemented. And what you've done is to supplement a big one, which I didn't think of until Dan's talk, really. And it has to do with what happens in a system in which you have some assortative mating that's there initially, before the speciation occurs. I always thought of that as a good idea for speciation, but it may not be, and that's what you've shown, and that's what's so important. It may actually be inimical to speciation if there's a certain strength to it. Consider the following. What really gets sympatric speciation going is not just the presence of weak fitness in intermediate phenotypes, it's the presence of negative fitness in intermediate phenotypes. There has to be negative fitness for there to be a possibility. And if there is negative fitness, the reason for the separation will be that the phenotypes on each side of the gap in fitness have a high probability of encountering and mating with each other and thus producing bad phenotypes in the middle. But if there are already some assortative mating present, and they are already avoiding the probability of seeing each other, mating with each other, and producing the intermediates, there is no reinforcement of the tendency to produce assortative mating and no further motion toward sympatric speciation. And that's really what I've learned from your talk, that one has to stop thinking of magic traits or combinations of ecology and mating as a one-way street. They may be useful, they may not be useful, and we need to have a lot more attention paid to the circumstances in which they promote speciation compared to the circumstances in which they actually slow speciation down.
I would also like to ask you a question or comment. I mean, first of all, I think I want to congratulate you on introducing this extra element in the process-based description of mating, which is gradually lowering aspiration level. I find that very plausible, and in higher organisms, that's exactly what you expect, and keeping it fixed so that they stubbornly try to find the mate that, according to all experiences have during the season, will never come around. At least in higher organisms, I think is implausible. I was, however, a bit surprised by the twist of your talk. I thought with that setup you would now look at the evolution of assortative mating and the costs of assortative mating now being mediated by this mechanism have changed, and therefore conclusions about these costs would change. So maybe I can recommend that as an exciting option for using your framework to answer other questions where I'm sure this process will matter.
Yeah.